Okay, any questions about what we did last week? Can we remember what we did last week? Guess we'll find out. The exam on Friday is going to be fairly similar to classes or to the old exams that are already on there. It'll match up the closest to any of the other exams. So you can use those as either additional problems or you can use them as practice tests. There may be a couple reactions on there, though, that we haven't talked about. So in terms of alkene additions, and we'll go through those. We'll go through those today.
I just had a question about the final. Which chapters are on the final? Someone said that only chapters 1 through 8 is on there.
That's for Dr. Kwan's class.
Oh, we still have all
12.
We have 12.
We're in chapter 12 right now. So in this book, alkenes is chapter 12, and the Wade book 8 is alkenes. So we just have a different spacing in the books. So the final will be totally comprehensive. But let's get through the third exam, and then we'll talk about the final next week.
Wait, are we gonna get like a roadmap like in the last test?
Yeah, I'll put something together before Wednesday. Okay, anything else? So you can use the third exam, 30 old exams from recent years, again, as practice. There are some additional homework problems for alkenes in the recent folders, and I'll put those in sort of a roadmap before Wednesday. The chapter 11 problems are due today. If you don't quite get them done before Wednesday. Again, you have so much time before now and Friday. How you want to use it is ultimately up to you. If you want to be doing chapter 11 problems or working on old exams, that's ultimately in your schedule. Wednesday, we will answer questions. I will answer any questions you want to ask, and if we stare at each other for more than 2 minutes awkwardly, then I'll just move on with alkenes. So
chapter 12 is not on the exam?
Part of it is. So the question is, what reactions could be on there? Well, let's go through the reactions that we've learned. So far we've learned that you can take an alkene and add what to it? How about HX? How about H plus H2O? How about H plus alcohol? What came next? BR2. BR2 and water. Of course, BR2 and water is just like BR2 and the alcohol. So even though we didn't explicitly do that, it's just changing an HOH to an ROH. And then I think that was it. Let me just double check. Here's the ones that I wrote this morning. Yep, same one. So let's talk about the next reaction. I'm taking these a little bit out of sequence like I normally do, but there'll be one reaction I don't think that I'll get to. And then we'll just get to it after the exam. So the next reaction that we are going to talk about is adding H2 across the double bond, and you need platinum or palladium as the catalyst. So we're going to add hydrogen. This is called a hydrogenation reaction. And so in this hydrogenation reaction, I'm going to end up adding 2 hydrogens across the double bond to basically change an alkene into an alkane. And so the role of the platinum and palladium is as a catalyst. And then for this, we'll talk about, the three things. What am I going to add? Two H's. How am I going to add them? Markovnikov or anti-Markovnikov? Well, that's done. Now we can move on to the third part. Wait. Why am I not concerned about Markovnikov and anti-Markovnikov? I'm adding a symmetrical reagent. So if I add a symmetrical reagent, what does that mean in terms of regioselectivity?
You have no choice.
I was thinking, is it or is it not regioselective? Can this reaction be regioselective? Why not? Because you're adding a symmetrical reagent. Right? So it's okay. I already stared as everybody didn't remember this from last week this morning. But whenever we have a symmetrical reagent, the reaction cannot be regioselective. So when we talk about regio and stereoselectivity, it's oftentimes easier to think about what cannot be regio or stereoselective than what is. So you can eliminate a lot of things by saying, okay, if you have a symmetrical reagent, either I'm adding two of the same thing or the alkene is symmetrical, that reaction cannot be regioselective. I can push this a little bit farther and say, when is a reaction not going to be stereoselective?
When you have an achiral reagent.
I always have an achiral reagent. It's a little more specific. Because this reaction could be stereoselective, but there's no chiral reagents. They're all achiral, right? So when will the reaction not be stereoselective?
If you have an achiral product.
True. If I have an achiral product, but looking at it from the reagent side, when will it not be? If you have a carbocation, what does that do to our third question? Remember, question number one, what two things am I adding? Question number two, Markovnikov, anti-Markovnikov. Question number three, 100% cis, 100% trans, or 50-50. When you have a carbocation, what does the reagent add? As far as the third question goes. 50-50. If it adds 50-50, can you end up with stereoselectivity? No. You can't. So it's easier to think initially about when the reaction cannot be stereo or regioselective, and then look at each one after that. So anything with a carbocation cannot be stereoselective. So let's just go back here. Okay, HX, carbocation, intermediate. Just say yes or no. Yes. Regioselective? No. Oh, sorry. Whoa, 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 whoa. Not regioselective.
While we're doing this on that day, can you also, like, as you do it, can you say what type of reaction it is?
Like, what do you mean, Markovnikov, anti-Markovnikov?
SN1, 1.
Nope. SN1 and E1 are not these reactions. These are all addition.
H2O with SN1.
No. The second step of the mechanism looks like an SN1, but it's not an SN1 it's not an SN1 reaction. These are all electrophilic additions to alkenes. That's their overall classification. So let me figure out what it just decided to do here. Normal, thank you. Okay, so stereoselectivity, no. H plus H2O, does it go through? Here, let's just make a table. Let's just make the table. And then we'll come back to the other reactions. Actually, we'll do the table. We'll do the table at the end. Keep everybody on the same page. We'll go through this reaction, then we'll go back and do the table. Or we'll go back and I'll ask you to fill in the table. Okay. I'm really tempted right here Faith and I just had a conversation about motivation. Not our motivation, your motivation. So, I mean, I hope everybody understands that there's a lot of stuff for Friday, right? So, you have to go through and organize it using your system. Okay. The last time I said, Friday is going to be a really hard exam, and then I got reviews like, he's taunting us. He's making it impossible for us. No. I'm just saying that the earlier we get to organizing things, the better. Right? So that's why when I'm asking these questions that we did last week, and I know it was 5 days ago, which seems like a long time, but you want to go back and make sure you organize. Maybe you're not at that stage of studying yet, but you should get there fairly quickly, I guess is my point. And I'm not taunting you. And I could write a killer test that got people 20% maximum, and I'm not going to do that. So you just want to make sure you organize things your way. So what I'm trying to do is give you these, tips. So if the reagent symmetrical can't be regioselective, let's talk about the hydrogenation, whether it's stereoselective or not. Then we'll go back, we'll add it into the reagents we have, and we'll write a table. So, how does this reaction work? Well, basically what happens is, if we have palladium or platinum, we have that as a metal catalyst. So we have pieces of platinum, pieces of palladium, and what happens is when the hydrogen comes in, it adsorbs onto the surface of the metal. Okay, adsorbing is a surface phenomenon. Ab with a B, sorbing is what paper towels do. It goes into the bulk. So this is a surface phenomenon. It's not totally quite understood, but what people think happen is that the hydrogen gas adsorbs onto the surface and then maybe breaks apart. Now, once the hydrogen is sitting then on the surface, the alkene comes down and the hydrogens add to bolt to one side of the double bond. And I can draw arrows to make it look like this. Double bond forming the CH bond to the left, the hydrogen bond breaking that pair of electrons using to form the CH bond to the right. That would take you through a transition state that looks like this. Okay, where I'm breaking the hydrogen-hydrogen bond, partially forming the carbon-hydrogen bond, and partially breaking the double bond. What's critical about this is now a square intermediate. And whenever you have a square intermediate, the hydrogens or whatever group has to add 100% cis. Okay, so this needs to add 100% cis. In the triangular intermediate, what did we have? We had 100% trans. So a square intermediate, we're going to add both groups to the double bond from the same side. And that means then that at the end of the reaction, both of the hydrogens end up adding cis. So we end up with cis hydrogenation. So you're not going to be asked to reproduce that mechanism. And when I show you this mechanism as well as the one for the next reaction, my goal is that if you get stuck on the exam and you go, hydrogen, does it add cis or trans? Then you may be able to say, okay, what happens? The hydrogen comes down, sticks on the surface. Okay, that means they add to the same side because they're going through a square transition state. So it can help you associate that with the idea that this is 100% cis. So hydrogenation then will add the hydrogens 100% cis. Okay. So then we have to ask ourselves a couple of questions in terms of, let's start with this one. So let's say we do this reaction, and I could very easily give you this reaction on Friday and say, okay, write the major product of the reaction, including stereochemistry where necessary. And then tell me if it's regio, stereo, both, or neither. So let's first of all deal with the idea of writing the product. So what I know is, I've got a CH3 attached to both carbons, and then I'm going to add what? I'm going to add 2 H's. So question number 1, hydrogenation, I'm adding 2 H's. Am I adding the Markovnikov or anti-Markovnikov?
Doesn't matter.
Exactly. There is no Markovnikov and anti-Markovnikov. How did I add them? Cis or trans? Or both? I add them cis. So what you can do then is give the hydrogens 2 bold wedges, and then by definition the methyl groups will get 2 dashed. If you don't like that, you can make the hydrogens 2 dashed, and the methyl groups will be 2 bold. Okay. So, my question is this. Is this reaction regio-selective? Is it stereo? And regio only, stereo only? Is it both? Or is it neither? So let me get a sense of where you're at. So is this reaction, this is the major product of the reaction, right? So is this reaction regio, stereo, both, or neither? And you can talk to your neighbor. Okay, go ahead and vote then. And then we'll go through and work this out.
And you said before, include stereochemistry. Does that mean we would have to show both of the options for products?
No, it just means you would have to show the major product. But that other product's probably going to come into play here.
Okay.
This would be what I would be looking for. If you wanted to write the other product, you could, but you'd have to write down and say, this is the major product. If you give me more than one product, you got to tell me which one's major.
Wait, so like, would there be a difference if you put the H's on the dash bunch?
No.
Okay, so
No, we can ask that. Well, I can ask you that. We can do that.
What's happening to the double bond?
It's disappearing.
Yeah, but why?
Because the double bond got used. Because the double bond got used to form one of the CH bonds. And then the broken HH bond got used to add the hydrogen to the other carbon. So when we've been doing all these reactions, the double bond's been disappearing. Whenever we add two things across the double bond, it always has disappeared. All right, let's see what we've got. We've got 2, 22, and 4. So 2, that it's regio, 22 that it's stereo only, and 4 that it's neither. Okay. So let's go back to our basic definitions. Is it regio?
No.
No. I mean, that was the first 10 minutes. If it's a symmetrical reagent, which we have 2 symmetrical reagents, there's no way it's going to be regioselective. But how do you know in general? Add the 2 hydrogens this way, add them this way. Did you get the same product? Yes. Can't be selective if there's only one product. Then neither. Well, the question is it stereoselective? So the other possible product here is to add the hydrogens 100% trans. I know they don't add 100% trans. I know that the reaction is 100% to 0%. But whenever you're looking at these reactions, Markovnikov, anti-Markovnikov addition along with 100% cis and 100% trans. You've got to write both sets of products so that you know whether they're different or not. And so if I write 100% cis addition, 100% trans addition, are those two different products? Yes. And what's the relationship between those two different products? They're diastereomers. Because the top carbon is the same and the bottom carbon is opposite. So these two are diastereomers. So this fits our definition of stereoselective. We have multiple products that are stereoisomers, specifically diastereomers. Did the reaction select one over the other? Yes. And again, it's like I said last week, it doesn't, stereoselectivity, the selectivity term, doesn't make a distinction between 100 to 0 or 51-49. It just says there's a majority product. And majority equals exclusive. There's no term for this is the only product we get. So when you're evaluating whether something's regioselective or stereoselective, for regioselectivity, add the groups both ways. Did you get more than one product? Yes. Did you select one of those as the major product? If the answer is yes, it's regioselective. For stereoselectivity, add the groups 100% cis, 100% trans. Are those two different stereoisomeric products? If the answer is yes, fine. Did it select one product over the other? Yes. So it's stereoselective.
And all the questions you're going to be answering is always going to be either 50-50 or 0 and 100, right? 'Cause there's no way we'd be able to know if it's not like perfectly 50-50 without like testing it.
Well, like Markovnikov addition. If it's Markovnikov, we're following the Markovnikov rule, which says that you're going to add the electrophile to the carbon with the most number of hydrogens. If you're tied on both sides, it's 50-50. And therefore it didn't select a product, it's not regioselective. So we have to follow Markovnikov's rule for regio, and then we're following 100% cis and trans for the other, for stereo. And one of the things with stereo here that I'll point out is your product must have two chiral centers for it to exist as diastereomers. If it only has one chiral center, because there's no chiral reagent here, it's 50-50 in those enantiomers. Yeah, it made a chiral center, but so what? It didn't select. So it's got to be both. You got to have two products, and you have to select one. Carolyn.
When you're talking about regioselectivity and the symmetrical reagents, do both reagents have to be symmetrical?
Just one.
Just one?
Just one. Because you could have, with this molecule right here, let's say I was to add HCl to it. I add H to the top, Cl to the bottom, and then H to the bottom, Cl to the top. I get the same product.
Okay.
So if one of those is symmetrical, it won't be regioselective. So then this reaction is only stereoselective. But then this is what I can do. I change it by taking away a methyl group. And I now ask you, what's the major product of the reaction? And is it regio, stereo, both or neither? So, write the major product and then tell me if it's regio, stereo, both, or neither. Okay, so there's my product. Now I just have to put in my wedges. And so the majority answer, it's neither. It's good. So we already knew it wasn't regioselective. And in this case, is it stereoselective?
There's only one chiral center, so you can't do it that right. Like if you do it that, there won't be another CH3. You can't have two CH3 attached because it's
no, there's just one CH3
attachment.
because it's this one.
Yeah, and then, and there's only one chiral center for that, or there's
I don't know. That was going to be my next question. My next question was going to be how many chiral centers are there? How many people say one? What'd you say?
Yeah.
How many people say 0? There's 0 chiral centers. Now how? Can do this a couple ways. First of all, these are 2 hydrogens, right? Just because there's bold and dashed wedges doesn't necessarily mean there's chirality. So they're gone. Because we would normally write them anyway. So a monosubstituted cyclohexane ring cannot be chiral. Because, so if we look at this, methyl's different than hydrogen, right? CH2, CH2. We move on. CH2, CH2. We move on. We end up in the same place. Therefore, this group and this group are the same. Don't like that approach? How about I draw a mirror plane? Mirrored plane goes right through the hydrogen, right through the carbons, and so therefore there are 0 chiral centers here. Either way, even if you mistook it to be 1 chiral center isn't enough. We need 2. Okay, so there's hydrogenation, and the reason, well, let's do the third reaction, and we'll maybe come back to that. Right, so hydrogenation, I'm adding 2 hydrogens, neither Markovnikov or anti-Markovnikov, 100% cis. Last reagent for the exam, but not the last reagent. And I'll have to go back to the previous reaction. This reaction is called hydroboration oxidation. Which takes me back to the previous reaction in terms of what is oxidation and reduction in organic chemistry. And those of you who had me in lab, when we talked about the yeast reduction, it was a reduction because I was adding hydrogens. So when we talk about oxidation and reduction, oxidation in organic chemistry means you add hydrogens or add oxygens or lose hydrogens. Reduction is you lose oxygens or you gain hydrogens. That's the basic definition in organic chemistry of oxidation reduction reactions. The issue in general chemistry is always about electrons. When we calculate the oxidation numbers of atoms in general chemistry routinely, we haven't done that yet, and we won't. It's not that it's that difficult, it's just it's not necessary. So since we don't do oxidation numbers, there's no need for us to use either oil rig or my personal favorite, Leo the Lion goes grr. For lose is oxidation, lose electrons oxidation, gain electrons reduction. And I think oil rig is the same thing, only the I doesn't mean anything. I'd much rather all three mean something. That's why I prefer the Leo the Lion thing. So that means that when we do hydrogenation, we're doing reduction. And as a matter of fact, if we think about what happened in lab, what we did was we converted the ketone into an alcohol by adding 2 hydrogens. And so we did a reduction here. And later, in next semester, we'll learn about what reagent it would take to add hydrogen across the CO double bond. It's not palladium or platinum, it's actually something a little bit more potent. But I can add 2 hydrogens across the CO double bond. And so if I would have done this in lab, I would have actually gotten a 50-50 racemic mixture. But that's what we did in lab with the yeast, was the yeast essentially added 2 H's across the double bond. But it did so using a chiral template in its own enzymes. So that's why we got a positive rotation out of that product. And that was a long time ago. But the report's due this week, so you'll have to refresh yourself. So when I talk about the oxidation part of this, I'm talking about hydrogen peroxide, because that's what hydrogen peroxide does. It oxidizes stuff. It adds oxygen to things. So this reaction is a 2-step mechanism. I'm going to show you. You won't have to reproduce it. But again, I'm showing it to you so it'll help you with the regioselectivity as well as the stereoselectivity. And this is the first reaction. It could be both. So here's what happens. When you add boron, when you add borane, this molecule is called borane. When you add that to a carbon-carbon double bond, the same kind of movement of arrows happens as before. Now, boron is less electronegative than hydrogen, which means the boron's slightly positive and the hydrogen's slightly negative. What happens is the pair of electrons can go from the hydrogen breaking the HB bond to go to form a CH bond, and then this pair of electrons can go to form the CB bond, the carbon-boron bond. So I'm going to go through the same type of square transition state that I just did. Which means that my hydrogen and my boron are going to add 100% cis. Now what happens to the boron when I add hydrogen peroxide to it? Well, when I add a hydrogen peroxide to it, it replaces the BH2 with an OH. And so wherever the boron was, that's where the OH ends up. And then, of course, the hydrogen that added. So it's a complete replacement of the boron with the OH in exactly the same position. So since this was 100% cis, the H and the OH added 100% cis. So could this reaction be stereoselective? It could. Now, what about the regioselectivity? Well, it turns out that the boron adds to the least hindered carbon. And then that means the hydrogen adds to the most substituted carbon. So this means that we're going to have anti-Markovnikov addition. And the anti-Markovnikov addition is just simply the opposite of Markovnikov. So the hydrogen's going to end up on the carbon with the least number of hydrogens, and the OH will end up with on the other carbon. So this reaction adds, if I go through and I summarize this, it's adding H and OH, anti-Markovnikov, 100% cis is how it's adding. And the boron, if we kind of consider it to be a larger group, it would want to add to the carbon that's least hindered. Now, the reality of this is that once you add your first hydride to a double bond, this BH2 is going to do that reaction with another alkene. And then the third is down to a BH. It's going to do it with a third equivalent of alkene. So one BH3 will react with 3 alkenes. And that means at the end, you're going to have a boron that's attached to 3 different alkenes, so it's going to look something like this. And that accentuates the idea that that boron has to add to the least hindered carbon. If I'm going to do this, two more times.
Wait, I'm confused because the alkene's symmetrical in the beginning, isn't it?
Well, I haven't indicated. I didn't write a specific group.
Oh.
So what I'm saying here is, if the molecule is unsymmetrical, then it's going to add, the boron's going to add to the carbon that's least hindered. In all the cases when I've done these reactions to begin with, I haven't specified groups. I just write a generic double bond, and then we go to the more specific double bond. So this one will add anti-Markovnikov.
What does the transition state with the peroxide look like?
We're not going to cover it.
Okay.
So the second step, you just have to believe me that, and you would be in trouble at this point if you didn't believe me, but I'm sure you could look it up on the internet. That's basically, since that reaction is more of an inorganic reaction, and this is organic. So we'll stay away from a lot of the inorganic stuff. But the key thing is, if it didn't replace the boron in exactly the same position, you wouldn't have the stereoselectivity that you have. Bobby?
So we were on so like, would you want us to write charges for this one other than the beginning?
Actually, what you're going to write for this one is you're just going to write the final product. So if I gave you a cyclohexene ring, if I said here, plus BH3 H2O2 and said, write the major product of this reaction, that's what I'm starting with, right? I just leave my bond out because now I got to figure out how I'm going to add it. So what am I going to add to the top carbon? First of all, if I'm going through this, what I would suggest is BH3H2O2, what am I adding? H and OH. Okay, H-OH. How? Anti-Markovnikov. So that means the bottom carbon gets the hydrogen? No, the top carbon gets the hydrogen. Then the bottom carbon gets the OH. And how did I add those? 100% cis, so let's put bold wedges on them, and then a dash for the methyl. And so that is the major product of the reaction. Anti-Markovnikov and 100% cis.
So on the exam, you wouldn't want us to write all the little stuff that you did.
No, I'm just showing you that to help you remember that the boron adds to the least sterically hindered, and that they added cis.
But this is the only exam. This is the only reaction that you want us not to write all the little stuff for. Or just specify on
The one
exam.
that we just did,
Yeah.
the hydrogenation. I will not ask you to do mechanisms for hydrogenation and for hydroboration oxidation. But the other ones that are on the list that I created at the beginning, they're fair game. Bromonium ions are fair game. Question. Regio, yes or no? Regio selective? Is this reaction regio selective, yes or no? Stereo selective, yes or no? Well, something to think about. All right, on Wednesday then, I I will answer questions. There's problems. I probably should not promise. Let's see, if I'm doing my job, I should probably write the roadmap this afternoon and then send it to you by email today instead of just waiting around until Wednesday, right? Because probably should have had it before Thanksgiving, but that's not happening. So there are a whole bunch of these problems where I've taken a cyclohexene, a methylcyclohexane, a dimethylcyclohexane, and an ethylmethylcyclohexene. I've taken those four and taken them through every reagent. Understand that if I change the structure just a little bit, I change the answer sometimes a lot as far as regio and stereoselectivity go. And that's in one of the folders. It's in one of the folders from last week and the week before. But I'll put all that together. So the reactions that you are going to be responsible for are these ones plus H2, palladium, and platinum, and also then the BH3, H2O2. So those will be the reagents that could be on Friday's exam. In the older exams, there may be some other ones that are thrown in, and in that case, those ones will come on the final exam. Okay. If you have questions, you can email me, stop by. Otherwise, I'll answer questions on Wednesday.